So number 9, now you can see basically has everything in it, right? And hydrogen, there's still a lot of hydrogen left. There's a lot of methane, and of course there is benzene and toluene, right? So you can see that obviously you're far away from complete conversion as obviously expected. There's a lot of hydrogen left, and that's why you have to work in hydrogen-rich atmosphere. And but you can obviously ask yourself, how do you know these numbers? Because these numbers are not coming from purely from mass balances. In some, yeah.
Can't you measure the actual? Can't you measure off portions of the streams different times?
Well, I mean, typically you're doing this before the plant is actually built, right? Because that's when the costing is. So yeah, these are all from design. That's what a design engineer will do for you. Yeah.
You scale up benchtop experiments.
So basically, yeah, you have to model the reactor, right? A lot of other streams are easy, like heat exchanger is easy. Those can just from mass balances, but after the reactor stream, you have to model the reactor. And somebody was asking last time about scale up, because yeah, frequently if you make predictions on a reactor based on benchtop data, you have to be very, very careful, because scale up is not trivial. You have to think very carefully on scaling up. And by carefully, I mean you have to think about the heat transfer, mass transfer, fluid mechanics, thermodynamics, kinetics, and how that could change. Are there any recycling issues? Are there any stagnation region issues? You have to really think carefully when you're trying to scale up from the benchtop data. All right, so anyway, those are your streams. This is your stream information. We already went through this. Oh, no, actually, I guess we didn't go through this. So these are the typical types of equipment that you deal with in your chemical industry. You can basically read it. There's really not that much to it. There are towers, there's heat exchangers, there are vessels, pumps, compressors, heaters. These are the most common equipment. Now, of course, you can see that you really don't have the separation systems described separately, but that's because most of them are in towers. So distillation column is a tower. Because you can see there inside the tower, you have number and type of trays, packing, and all this stuff. So distillation column is simply a tower. Liquid extraction is a tower. Okay. Just as you have a table to tell you exactly what every stream is, you have a table to describe what each equipment is. So like, for instance, E101, E is a heat exchanger, like we discussed, unit 1, zone 1 and first heat exchanger. It's FLH. Does anybody know what FLH is? Floating head heat exchanger. So when you do a heat exchanger class, you'll probably know what the different types of designs are. Shell and tube, floating head. It gives you the area, which you all probably know is the most important design parameter for heat exchanger. It tells you the duty. Duty is how much energy got exchanged across the surfaces of the heat exchanger. It tells you all the shell conditions or the tube conditions. Okay. Then the vessels, you can see vessel 101, 102. It gives you all the relevant conditions for that. Those are essentially just vessels. There are no stages in it. So the internals are there are really no internals in it, except tower 101. So tower 101 is basically a distillation column, right? So let's just look back at 101. So tower 101, you can see is a distillation column, right? So before that, all the towers there's nothing. We can look at R101, but I think even R101 is, let's look at what R101 is. But first, also, let's look at T101. No, T101. Okay, so T101, yeah, you can see there are 42 steam trays and 316 stainless steel. That's just the material. Stainless steel is the material, and the diameter is there. And then, of course, the reactor you can see is basically a catalyst packed bed, 10 meter. So you can see there's a catalyst in there. It's a packed bed of catalyst. Okay. The height and the length, height is that, diameter. So I presume 10 meters is the height of the actual catalyst bed, and 14.2 is the total height. Diameter is given. No, there are no further details regarding the type of the catalyst, but you would probably know that in some sort of supplementary material what exactly the catalyst is and what the cost of the catalyst. All right, so you know, so you can see that essentially what you have for PFD is you have an actual process topology, which tells you all the connections. Then you have a table for all the streams, and then you have a table for all the equipment. So those are only the three things that every PFD has. In some PFD, some of this information may be on the PFD itself, but usually you have separate tables. Yeah.
CS, this might be done. Is that commercial steel?
No, CS is carbon steel.
Carbon steel.
So this is what a picture looks like. So this is a more detailed PFD, the same PFD, except now you can see it has some more details in it, including some of the control loops, and also how the walls are controlled and things like that. Okay. All right. So any questions? I mean, I know I went through this fairly fast, but really there's not that much to explain. It's all just giving you information, which some of you probably already have it. Also, how many of you actually done internships? Okay, so I guess most of you must have seen something like this, right? No? How many of you have seen a PFD? Okay, so clearly some of you. Does anybody want to add to anything I said? Because I have never really worked in industry ever. So, I mean, I've done internships, so I guess I've seen a PFD, but if anybody here has something to add based on your internship experience, please feel free to say. Yeah?
So I hadn't seen that symbol for pumpkin before. I always saw it.
Okay, you saw like a circle and the.
E102 A/B over on the right there. Those kind of,
I think it's the difference between a displacement and a centrifugal.
Oh yeah. I think that these are two different types of pumps. Yeah. So I think if you go back to the table, I think it might tell you.
Because since it's toluene, they probably use a displacement pump.
Yeah, so you can see there are actually three different symbols depending upon pump, turbine, and compressor. Right, any other comment or information?
That last one isn't a compressor, that's a pump.
It's a centrifugal pump.
That's a centrifugal pump? Okay.
Yeah,
well,
the other
so I guess I think they probably use all of these for depending on different types of pumps. So this is a centrifugal pump?
Yeah, and the first one I think is a
It's a
displacement.
displacement pump. I guess that's a compressor. Yeah, that's a compressor. Yeah, this is definitely a compressor. I guess these two are pumps. Sorry? Depends on the
If it's getting smaller, then it's a compressor, getting wider, it's a
turbine. All right. Okay, should we move on? Okay, so that's all I have for, as I said, for just not for this class, but just for the pictures. Any questions about this? No? Don't read my emails. Close your eyes. Okay. Shh. So if you remember, at least for the purpose of this class, we are drawing these diagrams for costing, right? We are assuming that we are not designing. You'll do design in your design 2, and there you'll likely be asked to draw this process flow diagram for whatever you're designing. Unless you do IPPD, in which case you're not going to do design 2. So now we're going to start talking about capital cost estimate. If you remember, we already talked about how to get estimates for the entire plants. How do you get estimates for entire plants? Right, you use the scale of factor, right? And you use a cost exponent. What's the cost exponent for chemical industry plants?
subsidy.
No, that's a chemical engineering price cost index. So it's a cost exponent. Power, 0.6, right? You need to remember that. If there's only one thing to remember from costing, you need to remember that chemical engineering plants typically scale as capacity to power 0.6. If anybody's going to ask you a costing problem, question in an interview, that would really be it. Yeah? No, you don't have a question?
Sorry.
No, it's okay. Oh, he raised your hand? Yes? No? Maybe he has a question then. Okay. All right, okay, so that's called the order of magnitude estimate. Okay, so order of magnitude estimate, you just use information from previous plants, scale it by cost exponent of 0.6, to take into account capacity, then you use step C to take into account inflation, and get the cost. Okay? That's called the order of magnitude estimate. Then you do the study estimate. Study estimate is when you actually, so you can see that for order of magnitude estimate, do you need a PFD? No, you don't need PFD, right? Just a block flow diagram is sufficient because all you're interested in is capacity. So for study estimate, you actually need the process flow diagram. You look at it equipment by equipment, and you cost each and every equipment. You just add them all up, and therefore you get the total cost of the equipment. Okay? There are of course other factors to consider, and we'll talk about those costs when you start doing the study estimates. This is just the details of what I've already told you. So I'm just going to, by the way, I'll upload these slides on campus, but I already told you all this. This just tells you the accuracy that if you do a class 5 estimate is basically a block flow diagram as a actually order of magnitude. Class 4 you can think of it as a, so we are looking at the top two. So you can see if you think of how much effort it takes to do costing, if you think of class 5 as your control, as you know 1 unit, the effort that it takes for class 4 is 2 to 4, not too bad. But the class 1, which is really finally you eventually have to do class 1 if you're actually going to build the plant. And for that you have to actually get bids from actual contractors. That takes about 10 to 100 times the effort of the initial cost estimate based on the block flow diagram. Also, you can see that a class 1 estimate, this best estimate, is fairly accurate. It's within plus 6% to minus 4% of the actual cost. But you can see it's very expensive. So class 5 estimate for a chemical process is typically in the range of 0.015% to 0.3% of the total installed cost of the plant. So the high range, 0.3% of the total plant cost is just in the estimate. You can see the estimation, cost estimation is an expensive proposition. And that's why a lot of consulting companies, their entire job is just costing. Some of you, if you end up in design, you probably will be doing costings. Now, these costings are very expensive partly because of the data. Data costs money. Most of the companies you'll work for, they will have their own data which they will use. Big companies anyway. But if you work for a smaller company, you'll probably be subcontracting this costing to a bigger company which only does costing. But most of the big companies have their own data that they use. So anyway, you can see the only take-home message from this is that if you look at the order of magnitude estimate, it doesn't have much, its accuracy is not very good. You can see it could be its order of accuracy relative to the best estimate is 4 to 20. So at worst, it could be 20 times off compared to the best estimate. And the best estimate you can see is already plus 6 to minus 4. So you can see it could be close to 100% off. That means the actual cost might be double of what you've estimated, or half. But that's just the nature of the game. You know, if you're going to spend very little effort, you're not going to get very good answers. But those are okay, because when you get that number, you know it could be off, and you can take that into account when you start doing your analysis of whether the process will be profitable or not. Okay, so now, I already told you about this, that you take into account, this is the order of magnitude estimate. You take into account cost of previously built plants, and you take capacity and inflation into account. So you do production to the power 0.6. So the cost exponent is 0.6. So C is the cost, P is the capacity. I think last class I used A for capacity, but anyway, it doesn't really matter. So C2 over C1 is ratio of capacities to the power 0.6. Now for individual equipment also, this equation sort of works, except the cost exponent is not 0.6. So you could ask yourself, why is cost exponent 0.6 for the entire chemical industry? Why? Is there a theorem? Is there a law that sort of gives you the answer? Sorry?
Lots of data says that it's not.
Lots of data basically say that. And really the reason in some sense is if you look at the cost exponent for various equipment, some of them greater than 0.6, some of them are less than 0.6. So you can see a compressor 0.84, heat exchanger 0.59, vertical tank 0.3, lower 0.6, this 0.48. So you can see some of them are greater than 0.6, some of them are less, some of averages out to 0.6. So just a data. If you do all the estimates, and you can certainly do this yourself. One, if you do a process flow diagram and you do an estimate based on the process flow diagram, you can see how much that estimate differs from the one you could have just gotten by the block flow diagram using just the 0.6 factor. This is just representing the same information in a graphical format. If you look at the cost of an equipment versus capacity in a log-log plot, the data will be a straight line. Okay. All right, how to take inflation into account? As I told you, take inflation into account by using index. The most relevant index for chemical industry is SEPSI. There's another index called Marshall. There's actually a bunch of different indices, but the one that we use for chemical industry is this, SEPSI, Chemical Engineering Plant Cost Index. These are just the values of SEPSI over last 1996 to 2011. You can extend this to 2016. There's more data in the latest version of the book. So interestingly, as I told you, if you look at that, where do you see a very significant jump? Right? 4 to 444. That's 2002. No, was it 2003 to 2004? 2003, 2004.
Is that Bush?
Is that Bush? No, it's not. That seems to be. It was Bush, yeah. It was Bush, yeah. So I guess this doesn't go all the way back into the Carter days, but if you go back further, you will see another jump, right? Yeah, so I think, so I don't know why there was a, you can go back and look at why there was a very big jump, 396, 402, 444 in 2003. Was that when the market collapsed? Or, but anyway, it's just very interesting.
Same with 2005 to 2006. It's like a
yeah, from 460 to 500. So you can see there's a 10% jump over 2 years.
07 to 08.
Actually, no, yeah, 402 to 500, there was a 100% jump within 3 years. So yeah, that seems like it was kind of,
And then decreased.
around 1996, it was actually very, very stable. That was Clinton president. Anyway, you can look into it and you can try to correlate it to ASUS. Okay, now you could ask me, okay, how do you get this SEPSI? Just like, sometimes every once in a while you'll really hear like inflation rate was this was inflation. What does it mean? What does it mean? Inflation is 2% right now.
We're printing more money.
Inflation doesn't necessarily have to mean you're printing more money. What does inflation mean? Now, what does 2% inflation mean? But cost of what? You buy like, I don't know, thousands of things, yeah?
There's more of something, so it's worth less. So essentially, if you
Yeah,
print more
but
money,
if you say 2% inflation, that means the cost increased by 2% in that year. The cost of what? Weighted average. There is actually a basket. It's actually called a basket. And what goes into that basket is already decided by the government. So there's a very specific things that actually go into that basket. You find out the price of each of those. I don't know how you find the price of that because it's all variable, right? Or depending on geography. So I have no idea how they actually calculate inflation. But nonetheless, they somehow figure out the cost of each individual thing in that basket. They average it out. This is how they do SEPSI. In SEPSI also they have a basket. This is the stuff that goes into the basket. You put certain weightage on that, and that's how you basically figure out the total value of the SEPSI. So this is just an example of how you take SEPSI into account. I mean, it's so trivial, I'm not even going to actually bore you with it. So all you do is well, I guess I'll just tell you anyway. So let's say the C2 is the cost at time 2, C1 is the cost at time 1. I2 is the index at time 2, I1 is the index at time 1. You just use this equation, right, to scale up or down the cost. Okay, this is an example. I guess we can do this example. It's somewhat more interesting. So let's say that you purchase a heat exchanger. I'm going to ask you to do this yourself without actually looking at the solution if you don't mind. I don't know if this is pretty difficult, but I don't know how else to do it. So you purchased a heat exchanger with 500 meter square area in 1996 for $25K.